Hey kiddos, here's the review for Spiral 9. We're going to start off with some chain rule type stuff. And our first problem has some kind of symbolic derivatives. So it's going to look really confusing, but it's actually going to be a little bit easier than what we need to do. So the first thing that we're told is that the derivative of f of x is g of x, okay? And then the derivative of g of x is f of x squared. Okay, that's kind of weird. What we're asked to find... Okay, so the second derivative of f of x cubed. Let's just see what this happens as far as the derivative. So the derivative of f would be f prime of x cubed, and then because we have a function on the inside, we have to do the chain rule times the derivative of x cubed, which would be 3x squared. All right, so the first thing that I notice here is that I've got f prime, and the derivative of f of x, aka f prime, would be g of x. I'm going to rewrite this as g of x cubed times 3x squared, and that's equal to the first derivative. So that's d dx of f of x cubed. Problem is, I need a second derivative, so we've got to take the derivative again. And when I take the derivative a second time, now I have a product rule, because I have two things being multiplied. So let's do this out. So that's going to be the second, 3x squared, times the derivative of the first, which would be g prime of x cubed, multiplied by 3x squared because of the chain rule. And then I'm going to do this as the first, g of x cubed, multiplied by the derivative of the second, which is going to be 6x to the first. Okay, so let's do some combining of things and see what we can do. So g of x cubed, I think, is okay. That's just going to be 6x g of x cubed. For the other piece, let's see what we got going on here. We've got a 3x squared and a 3x squared. That's going to be 9x to the fourth. And then I've got g prime of x cubed. Okay, let's see what we got as far as things that look like answers. I've definitely not A, B, or C, because those are all just kind of singletons. Leaves me with D or E. That doesn't look anything like E. D looks like it might be right, but they've got f of x to the sixth. So let's see where that is. Okay, so if the derivative of g of x is f of x squared, oh, so that's this derivative. So this would be f of x squared, and then that something squared would be x to the third, because that's what's inside here. That's where that f of x to the sixth comes from. Okay, definitely D. For number 2, I've got to take the derivative, and I have a definite product here, where I have a first term and a second term. There's also a clever way to do this that I might talk about in a minute. Let's do the product rule first. So this is going to be the second, the square root of 2x minus 3, times the derivative of the first, which is 1, plus the first, x, times the derivative of the second. And I'm just going to write this as the derivative of 2x minus 3, and then to the 1/2 power. Okay, nothing to do with that first piece, so that's 2x minus 3. And then over here we've got a power rule. Let's bring that 1/2 down. And that's going to be 2x minus 3 to the negative 1/2. And then the derivative of the inside would be times another 2. The 1/2 and the 2 cancel out, which is kind of nice. And now we've got the square root of 2x minus 3. And over here, this is going to go on the bottom. So it's x over, and the positive 1/2 power would be just the square root of 2x minus 3. And that doesn't look like anything that we have here. let's find some common denominators. This is over 1. I'd like it to be over the square root of 2x minus 3. So let's multiply this by the square root of 2x minus 3. On top, that gives us 2x minus 3 over the square root of 2x minus 3. And that's plus x over the square root of 2x minus 3, which is going to be 3x minus 3 on top, square root of 2x minus 3 on the bottom, which happens to be a. I had tried to take a look at another kind of cool way to do this by combining those into one at the beginning, and then that ended up making a mess, so I'm not going to go down that path, and you can ignore that. For the last one on this page, we're looking at f of x equals 2x plus 1 to the fourth. We're going to find the fourth derivative. The goal here is really focused that this is a chain rule. So we're going to start with 4, this is going to be f prime. Ooh, we're going to change colors by accident. 2x plus 1 to the third, and then times 2 for the chain rule. I'm going to rewrite that as 8, 2x plus 1 to the third. And then f double prime, excuse the bell, would be, bring the 3 down, we get 24. And then we get 2x plus 1 squared times 2 for the chain rule, which is the same as 48 times 2x plus 1 to the second. The third derivative, f triple prime, would be 96. And that's going to be 2x plus 1 to the first times another 2, which is going to be 192 times 2x plus 1. And then we're going to have a fourth derivative. And when we do that, it's just going to be 192 multiplied by the derivative at the inside, because there's nothing left there, which is 2. 384 would be your final answer, which is E. Next up, we've got some implicit differentiation and logs. And as far as the implicit differentiation stuff, pretty predictably, you're going to see a question like this in some form. Either directly like this or one that you might have to plug some stuff into. There are a couple things to keep track of. The first is that we know there's going to be a product rule because we like testing you and making you worry about that, and that's always going to be there. And the second is that every time you take a derivative that involves a y, you need either a y prime or a dy dx. I'm going to use dy dx today just to throw some variety in there. It's more annoying to write, but it can help as far as understanding that that's what you're trying to get at the end. So we'll see how that goes. Okay, first up I've got to take some derivatives. Derivative of x cubed is going to be 3x squared. I've got my product rule, 3xy, so the first times the derivative of the second is going to be 3x times the derivative of y, which is dy dx. And then I'm going to have 2y cubed. That's going to be plus 6y squared. And again, whenever we do a derivative that involves y, it's going to be dy dx. And then the derivative of 17 is going to be 0. We also know we need to gather all of our pieces onto one side. Did I just miss half of a product rule? I sure did. That's what happens when I don't pay attention. So we did the first times the derivative of the second. We did not do the second y times the derivative of the first, which is 3. Sorry for that, making this even more confusing. We got to get the dy dx stuff on one side. Both of those are positive, and I kind of like having them stay there, so let's get rid of the other stuff. I'm going to minus 3x squared to the other side. Same thing, I'm going to minus 3y. And on the left side, we're left with 3x dy dx and 6y squared dy dx. I can factor out a dy dx. And when we do that, we get negative 3x squared minus 3y. Last part, let's divide by 3x plus 6y squared. And when I do that, we get dy dx is equal to negative 3x squared minus 3y, lots of 3's in this, huh? Over 3x plus 6y squared. Woohoo! And I look for my answers and it's not there. Oh, man, did we do this wrong? No, we can just do more stuff with this fraction. Like I know that everything on top and the bottom could be divided by 3. Hey, you thought I just mentioned 3's for jokes, but I didn't. It's part of the problem. And when we divide everything by 3 on the top and on the bottom, what we end up with is negative x squared minus y over x plus 2y squared. Okay, now I look again and I still don't see the problem. Okay, well, let's get rid of some answers. I know it can't be E or D because those have weird things that are not that. C looks pretty close, but I've got a y squared in the bottom, not a y. Oh, we're down to A. Okay, that's kind of interesting. But they've got a negative out front, and oh, they factored out a negative, and on the top, both of those became positive. That's where that answer comes from. Okay. Number 18. Oh boy, there's not a lot of room here, so I'm going to zoom in and give myself some more room. So I've got the natural log of 2x plus y is equal to x plus 1, and we've got to figure out what dy dx is. I've got a couple different options here. The first is I could take the derivative of this and then have to do some work in terms of some implicit things. The other thing that might be interesting is I could convert this into exponential form, and that might help me deal with this. So if I do that, I know that natural log, and if I do this as natural log of like u, is equal to, I don't know, v, because why not confuse you with letters that looks kind of similar, that e to the v is equal to the inside of that log. So in this case, that would be 2x plus y is equal to e to the x plus 1. And, you know, I think to me that looks a lot easier to take the derivative of, because we've got the derivative of 2x is 2. The derivative of y is dy dx, or y prime. And the derivative of e to the stuff is e to the stuff, and then multiplied by the derivative of the stuff, which in this case is just 1. Getting dy dx by itself, we get e to the x plus 1 minus 2 is equal to dy dx. And just to take a look, let's see if we have that as an answer. Ooh, we don't. They totally wanted us to do this implicitly, but I think that's a much more elegant answer. Okay, well, I guess I'm going to leave that. Normally I might go back and erase that if I got to an answer that was nothing to do with the problem. But I think that's a much better way to do this. And if you happen to do this on your spiral, and they were like, what the hey, I don't know what's going on. To be honest, I'd probably give you full credit for that, because you did an awesome job getting to this point. So let's look at this another way, and just start by taking the derivative. So that would be 1 over 2x plus y, multiplied by the derivative of that stuff, which is going to be 2 plus dy dx. And that's equal to 1, because derivative of x plus 1 is just 1. I'm going to multiply the 2x plus y to the other side, and I get 1, that's this one, times 2 plus dy dx is equal to 1, that's this one, times 2x plus y. So when I do this out, we get 2 plus dy dx is equal to 2x plus y. And when I get dy dx by itself, I get 2x plus y minus 2, which does happen to be one of the answers. I don't think that's as interesting as the one that we had to start with, but hey, I think that our method was pretty awesome. Okay, and just as a side note, you may happen to notice that e to the x plus 1 is equal to 2x plus y. And if you happen to notice that here, you could have substituted that in and not have to do this a different way. That's kind of cool. Okay, 39. We've got y is equal to the tangent of u. U is equal to v minus 1 over v, and v is equal to ln of x. What is the value of dy dx? Ugh, this is kind of a mess, huh? Okay, well, I'm going to not substitute things in just because I think that there might be some kind of cool things we can do symbolically to make this a little bit less stressful for us. We know we need dy dx. I'm going to take the derivative of y is equal to tangent of u. Let's see what happens. So that tells me that dy dx is equal to secant squared of u, and then I've got to multiply this by the derivative of u. Okay, I'm going to plug my u's in because I might as well. So you got dy dx is equal to secant squared of v minus 1 over v, ugh, and that's multiplied by the derivative of that, because that's what u is. Let me give myself a little more room. And the derivative of that is going to be one times dv dx. In other words, the derivative of v minus, well, it's v to the negative 1. So negative 1 v to the negative 2 dv dx. In other words, the derivative of v. Now let's plug our v in. So we've got dy dx is equal to secant squared of ln of x minus 1 over ln of x. And that's going to be multiplied by 1 times the derivative of ln of x, which is 1 times 1 over x. Minus minus is plus, and that's going to be 1 over ln of x squared. And then that's going to be also times 1 over x, because that's the derivative of v. Okay, that's really gross. I wonder if there's a better way to do this for my second time through, because obviously I'm going to try to do this again. So we've got secant squared ln of e minus 1 over ln of e times 1 over e plus 1 over ln of e all squared times 1 over e. Okay, well, good news. Ln of e is equal to 1. So we really got secant squared of 1 minus 1, which is 0, times 1 over e plus 1 over 1 squared is 1, times 1 over e. Okay? Secant squared of 0 times, that's 1 over e plus 1 over e, which would be 2 over e. And then finally, well, secant squared is 1 over cosine squared, and cosine squared of 0 is 1. So we get 1 times 2 over e, which is just 2 over e. That seems like a lot of work for kind of a simple answer. I wonder what would have happened if we had started out by plugging these functions in. Well, let's see. If we start off with plugging things in, we get y is equal to tangent of u, which is y is equal to tangent of v minus 1 over v, which is y is equal to tangent of ln of x minus 1 over ln of x. Okay, so now if we were to do the derivative of tangent, would be secant squared of ln of x minus 1 over ln of x multiplied by the derivative of this stuff, which would be 1 over x minus 1 over ln of x is really ln of x to the negative 1, so it'd be negative 1 ln of x to the negative 2. Then when you plug e in, you get secant squared of 1 minus 1 is 0. So you still have the same thing we had before, and that's going to be 1. And then for the other part, we're going to have 1 over e, and that's minus 1. Ooh, I also forgot to do a chain rule here. The derivative of ln of x would be 1 over x for that last chain rule. And then we're going to have 1 over e as well. Positives, and we also end up at 2 over e. I don't know if that's faster because it wasn't kind of stepping through it piece by piece, or if it actually is faster. I think that both of those are kind of gross as far as ways to do this problem. I don't know that there actually is a good way. Okay, and the last part, slope of the line tangent. I need to think derivative. So I'm looking for derivative of this thing. That's a quotient rule. So we've got the bottom times the derivative of the top, which is e to the stuff, times the derivative of the stuff, which is negative 1, minus the top, e to the stuff, times the derivative of the bottom, 1, over the bottom squared, x plus 1 squared. I might plug in 1 now before I try to simplify, just because I'm feeling kind of saucy, and let's see where that goes. 1 plus 1 is 2. E to the negative 1 minus, that's times negative 1, so let's make this negative 2. Then we're going to be minusing e to the negative 1 times 1. And on the bottom, I plug 1 in, I get 1 plus 1 is 2 squared is 4. Okay. So negative 2 minus another one would be negative 3e to the negative 1, because we have 3 of those things, over 4. And I don't see that as an answer. I do only see one of these that has negative 3 over 4 as part of it, and that's just to remember that we've got a negative exponent. Therefore, I could rewrite this as negative 3 over 4 multiplied by 1 over e, which does give you the same thing as choice B. All right, we've got some RAM stuff going on, some rectangular approximation methods. And what we're going to do here is to find stuff, in this case, with trapezoidal approximation. What that means is we have to, so if we're using 4 intervals, we're looking at these guys, 2, 3, 4, and we have to think about the y values here as the bases of the trapezoids. Each width appears to be 0.5, so in terms of trapezoidal area, all of these are going to look kind of similar. You've also got to show me this step. You have to show me these intervals and what's going on here. So we know we need 1/2 times base 1 plus base 2, 3 plus 3, and times an interval of 1/2. That's my first one. I'll do a second one in different colors so we can keep these separate. 1/2 times 3 plus 5 times 1/2 for the width of the interval. We're going to have 1/2, 5 plus 8 times the width of the interval, which is 1/2, and then 1/2 times 8 plus 13 times 1/2. If this were not a multiple choice question, you'd be done. You could take this as far as this and be totally happy. I'm going to multiply in each case 1/2 times 1/2 and write that as a 4th out front of all of these. So 1/4 of 6 plus 1/4 of 8 plus 1/4 of 13, and then plus 1/4 of 21. Okay. I'm also going to do some math-magic because I don't have a calculator in front of me that is charged. And I'm going to factor 1/4 out of this whole shebang. And we get 6 plus 8 plus 13 plus 21. So 6 plus 8 is 14. Then we get to 27. And that takes us to 48. 1/4 of 48 is going to be 12. Value of 0 to 7, integral f of x dx. So they're asking for the accumulated area here. We got to be a little bit careful because we're going to have some positive area. And that's going to be this trapezoid. That's going to be this rectangle and this triangle. And we're going to have some negative area, and that's going to be this triangle down below. So let's do this first part. So triangle down below, that's 2 by 2 times 1/2 is going to be -2 for that area. Triangle on the right is going to be 1 by 2 times 1/2 is an area of 1. The rectangle, I guess this is a square, is 2 by 2. That's going to be 4. And I might break this trapezoid up into a rectangle, which is 2, and a triangle, which is 1, to make myself a little bit easier. So you got 2 plus 1 is 3, plus 4 is 7, plus 1 is 8, minus 2 would be 6. Next up, we've got some integral properties and the FTC fundamental theorem of calculus. So in terms of what's going on here, they're giving us some kind of a functional expression, and then they're telling us to use that with some kind of other piece. The first thing we can work out here is I can break up this integral into 2 parts. The first part is going to be the integral from a to b of f of x dx, and the second part is going to be the integral from a to b of 5 dx. You could certainly do this algebraically, but it might be easier to think about this as an area problem. We know that the height of 5, and if we're going from A to B, this area would be the height, 5, times B minus A, the width. So that would be the 5 part, and that would be This is a different color. 5b minus 5a. We're told what this is. It's a plus 2b. So when I combine those, we get a plus 2b plus 5b minus 5a, which is going to be 6a minus 3b. And I don't see that anywhere. I wonder if I added wrong. And I totally did, because I combined the wrong like terms. Because a plus negative 5a is actually negative 4a, and 2b plus 5b is actually 7b. I combined a's and b's. Woohoo! For the next one, we've got to do some antiderivative work. There's going to be a nice shortcut that we can do to kind of make some of the problem with this go away. And that's going to be looking at breaking this up into two pieces. So we're looking at the integral from 1 to 2, x over x squared, and then minus, sorry, I need my dx, the integral from 1 to 2 of 4 over x squared, which we'll call 4 to the negative 2 dx. Okay. X over x squared, I can reduce to be 1 over x. I know 1 over x is the derivative of ln of x. So if I'm looking for an antiderivative of this would be, so ln of x, the interval from 2 to 1. So ln 2 minus ln 1. That's my first part. Second part, I'm going to increase the power by 1. This is the reverse power rule. So that's going to be from negative 2 to negative 1. 4x to the negative 1 divided by the new power, which is negative 1. And again, I'm going to plug in both of these points. So that's going to be 4 over x, or negative 4 over x. I might just take care of that negative with this, but let's keep it in for now. So negative 4 over x when x is 2, and negative 4 over x when x is 1. When we do that, we get negative 2 plus 4, which is 2. So from that, we're going to minus 2. We get ln of 2 minus ln of 1 minus 2. And I don't see that as an answer. Oh, boy. Oh, but ln of 1 is just 0. So this middle part can go away, leaving you with just ln of 2 minus 2. And then finally, we get number 25, accompanied by yet another bell. And here we've got a function defined by an integral, and we're asking for the derivative. I'm just going to write this out at first. So the derivative of the integral of 1 to x of 1 over t dt. There's a shortcut that we can absolutely do for this, and that's to understand that we're taking the derivative of an antiderivative, and when we do that, we just end up with the function on the inside, multiplied by the derivative of x, which happens to be 1, which is just 1 over x. If we were to do this piece by piece, the first part that we'd have to do would be to do the antiderivative of 1 over t. All right, so what function has an antiderivative of, what function has a derivative of 1 over t? I'll leave the derivative sitting out front for now. That function would be ln of x. We have to use the absolute value for domain purposes. So we'd be talking about the ln of the absolute value of t, and we're going to evaluate that at x and at 1. So this is the derivative of ln of x minus ln of 1 which we talked a minute ago is just equal to 0. And the derivative of ln of x is 1 over x. Either way is okay to complete this problem.